Hello, space enthusiasts. Welcome to the future of satellite technology in planetary discovery, Galactic AI 2024, brought to you by the Satellite and IT Division of SETS or USL. I am Kavisha Sandani, and alongside me is my dynamic co-host, Vagisha Abesingha. We are absolutely thrilled to have you all here today as we embark on this exhilarating journey into the cosmos and beyond. Get ready to dive deep into the cutting edge world of satellite technology, where innovation meets exploration. Together, let's push the boundaries of what we know, share our passions, and ignite our curiosity. So, buckle up, it's going to be an unforgettable ride.
To officially start our event, I'm excited to introduce the Vice President of SETS OUSL, Rivindu Yahampat, to deliver the welcome speech. Over to you, Rivindu.
Good evening, everyone. I am William, the Vice President of SETS OUSL, and it is my absolute pleasure to welcome you all to Galactic AI'24, organized by the Satellite and IT Division of SETS OUSL. Join us today on a thrilling journey through satellite technologies, explore our innovations, present advancements, and the latest with the AI in space exploration. To start, I would like to extend a warm welcome to our esteemed guest speaker, Mr. Lahiru Udara. He holds a Bachelor of Science Honors in Mechanical Engineering, specializing in mechatronics from the University of Morocco. Mr. Udara is also a mechanical engineer and support engineer at Robotic Assistance Devices. His hands-on experience and academic and his contributions to the field. I would also like to welcome our University of Advisors whose guidance and support have been instrumental in making this event possible. A special welcome goes to all the SETS members, the OUSL members, and members from other SETS structures. Your presence here today underscores the collaborative spirit and shared passion for space exploration that unites us all. Welcome all University and school students. Your curiosity and eagerness to learn are the driving forces behind events like these. Lastly, I extend a heartfelt welcome to everyone else who has joined us today. Your interest and participation are invaluable, and we are grateful for your presence. Once again, welcome you all to Galactic AI'24. Thank you for being here.
And now the moment we have all been waiting for. I'm thrilled to introduce our guest speaker, Mr. Lahiru Udara. He's a mechanical engineer and support engineer at Robotic Assistance Devices, bringing a wealth of experience in mechatronics and satellite technology. Mr. Udara's insights are going to spark our imagination and propel us into new frontiers of knowledge. Mr. Udara, the stage is yours.
Thank you everyone for the kind welcome, and I want to thank the organizing committee of this session, the SETS OUSL. I have to tell right about a few minutes ago, there's a power cut in my area, so unfortunately I cannot turn on my camera because it's dark here. Let me share my screen, and I hope you can see my screen clearly.
Yeah.
Okay, thank you. So today I will be discussing about the topic here in English language, but if you guys cannot understand what I'm saying in English, or if there's any issue on that, you can ask about that in Sinhala. In the chat box, you can ask. I could understand that. Can you explain that in Sinhala? I will. So that's not a problem at all. So today we are going to talk about planetary discovery and how the future of the planetary discovery will change with the upcoming new technologies. Okay, before going into the planetary discoveries, we are focusing on how we discover planets, specifically exoplanet. That means planets in other solar systems, outside our solar system, planets orbiting other stars. So we are focusing on satellite technologies that are used to discover exoplanets. So before jumping into the discovery part, first I am going to talk about satellite technologies. So basically a satellite is a spacecraft that is orbiting the Earth. So in satellites, there are major subsystems. I'm going to go through this quickly. So the main thing is the structure. That's mean kind of the skeleton of the satellite. This holds the rest of the satellites together. So it's kind of the body of a human being. So when we are building a satellite, our main focus is to develop a structure with the least mass, because when we are going to the space, we need to make everything as lighter as possible. So making the structure as light as possible is one of the key challenges when building a satellite. So here is like a internal photo of CubeSat, which is a small satellite. So you can see how tightly packed inside the satellite. As I said, so these are some pictures from inside. There are a lot of components inside satellite, and it's all packed together to make the final. We need power, and we get electrical power from solar cells or solar panels. There are few satellites that use nuclear power, but those are mostly military satellites, not civil applications. So the majority of satellites are working on solar panels. And one of the key things is the GNC, or guidance, navigation and control of a satellite. That means how we control the satellite, how we turn a satellite, how we determine which direction I'm facing. Because now we are going to talk about planetary discoveries. So that means we have to observe other stars to find if there's any planets orbiting that star. So in order to do that, we have to focus our camera or our telescope we're observing. So in order to do that, first we need to determine which way I am looking at. And then if it is the wrong direction, we have to turn the satellite, or turn the camera, which is set to the satellite, towards the star that we need to observe. So first thing is determining where we are looking right now. Then we need to determine which way I need to look at. Then we need to turn the satellite. So that process is called guidance, navigation and control, or we call it GNC. So to do that, we use a lot of sensors. So one of the main thing is the IMU, which is the inertial measurement unit. These sensors are actually contained in your mobile phones as well, but kind of different kinds. But what this basically does is it can detect accelerations and rotations. So if you know physics, if we know acceleration, we can calculate velocity. And if we can calculate velocity, then we can calculate the distance we are moving. And on the rotation side, if we know the angles in like XYZ direction in the space, we know which way we are looking. So that's the role of IMU, or Inertial Measurement Unit. And then we have star tracker. Star tracker means it's kind of a little camera. It identifies bright stars in the sky. So like kind of Sirius, Aldebaran, Rigel, and bright stars. So if we know in which direction, we can kind of get an idea. Okay, if we can see Sirius star in that direction, and if we can see Aldebaran in that direction, that means we are facing this direction, and then we can rotate the satellite to face the direction that we need to see. So it kind of read like that. I am explaining this in very simple terms. Then we have sun sensors. So it looks for the sun. So if we know which direction the sun is, we can get an idea where to turn our telescope as well. So all of these sensors are used to determine which way which direction we need to turn. So that's the process here. Then how we turn the satellite. So basically, we use basically 3 types of actuators to rotate a satellite. So one thing is thrusters. Thrusters means small rocket engines. We discuss on this later. And reaction wheels are mostly used on small satellite and space telescopes, which we are interested in right now. So reaction wheel is kind of a wheel and a motor. So if we turn the wheel, it creates a torque around the motor as well. So it will turn the motor and the satellite on the other direction. So it kind of like this. Let's say this is the satellite, and we have a motor attached here, and there's a wheel attached to here. So if we turn the wheel in this direction, the mass of the wheel will turn the satellite on this direction. So if we want the satellite to rotate like this, all we have to do is turn this wheel to this direction. It's kind of simple thing. Using these reaction wheels, we can precisely turn a satellite without using fuel, and because thrusters use fuel, but reaction wheels doesn't. And magnetorquers are basically using the magnetic fields of the Earth to turn the satellite. It's kind of using like 2 magnets. If we use one magnet like this, okay, here we have a magnet. Let's say this is the north side and the south side, and if we have another magnet closer to that, it has south here and north here. These 2 direction will kind of repel each other. So in satellite, using magnetorquers, Earth has a magnetic field. So let's say south and north. And in satellite, we have electromagnets. So in electromagnets, we use using electromagnets, we can like change the polarity of the magnet. So if you make no toward that, so it will turn the satellite in direction. So this is like a very simple way of operating, but is more complex than this, obviously. So these types of actuators are used to turn a satellite. That is essential when you are using a satellite to observe planets. And of course, the propulsion of the satellite is one of the key thing. propulsion in how do we move in space? We have to adjust our orbit and move to another orbit, those kind of things. So basically, cold gas thruster is a very simple way of doing that. Cold gas thruster means inside a bottle, and using a small valve and a nozzle, you can just eject that gas out of this nozzle, and it creates the force as we want. And the next step would be chemical propulsion, burn those liquids. Sorry about that, guys. With the power coming and going, it had an internet connection. Fuel and oxidizer to burn inside the combustion chamber and eject those gases, so it will create force on the satellite. And the one of the most efficient rocket propulsion is using electric rocket propulsion. That means an ion thruster. You get a gas, most probably a noble gas, and you separate the ion and electrons using a magnetic field or electric field, and you can eject those ions and electrons in very high speed in one direction, so it will create a force in other direction, which is exactly a rocket engine. So this ion thrusters or electric propulsion is a very efficient way to change the speed of a satellite. So nowadays we are seeing a very big increase in numbers of satellites that use electric propulsion. And one final thing is telecommunication. So we need to communicate with the satellite in order to get data from the satellite, and we have to send commands to control the satellite, and we have to get data from its payloads. And thermal management. This is something people don't usually talk about when we talk about satellites. So thermal management is very important because when we are in space, we have to face the intense heat from the sun, and there's no atmosphere to protect the satellite. And if we are in Earth orbit, we are going around the Earth, and we go from the daylit side to night side very quickly. There's no like morning and evening. It's a very sudden difference in temperature. It goes from like hundreds of degrees of Celsius to minus 60 degrees of Celsius when you are going from the bright side to the night side. So the temperature difference and the gradient is very high. So every satellite needs a thermal management system. Otherwise, it would overheat and freeze. And if this thermal cycles goes for a few times, it will damage electronics and internal components. So thermal management is very, very important for the longevity of a satellite. And the most important thing of the satellite is the payload. Payload is the system that we use to get things done from a satellite. So the rest of the thing that I explained earlier, that is for just the operation of the satellite. We need electrical power, we need propulsion, we need guided navigation, and everything that I need to operate the satellite. But what do we do with the satellite? That's the important thing. So that comes down to the payload. Now, I think all of you guys have heard about Starlink satellite. That's managed by SpaceX. Those satellites are used to provide internet connections all over the world, and the payload of those satellites are basically antennas and communication devices that provides internet access. But if we are using a satellite to discover planets, we need powerful cameras. So this satellite is not a very big satellite. This is a Planet Labs Dove satellite. It has a small telescope, and it's used to observe the Earth. But we are talking about observing the other direction towards the space. So let's see about that. So how do we detect or discover other planets outside our solar system? Because in solar system, we know what we already have. There are 8 planets and hundreds of small solar system bodies that includes comets, dwarf planets, asteroids, and all of these things. But astronomers are very focused on detecting planets outside our solar systems. So it is a very difficult task to do. It's very challenging. Yeah, I think someone has raised hands. Maybe yes, question or something.
Excuse me, sir.
Yeah.
When you're detecting an exoplanet, normally what scientists do is, so mostly exoplanets have a sun, right? The star they are orbiting. So what they do is so when the planet is passing through the sun, it makes a shadow, like a dark patch. So with that, they can calculate the mass of the planet and stuff like that and find the planet. Is it how it works? So
That is one type of detecting planets. That's exactly what I was going to explain. So one of the earliest methods that used to observe exoplanet is called radial velocity method. Um, this doesn't need this method doesn't require a very powerful telescope. I will explain why. Because now imagine there's a planet orbiting another star. So due to the mass of the two system configuration, the star is actually moving along the barycenter of the two system. So if the mass of this planet is very high, the motion of the star is also very high. So I think in our solar system, Jupiter has the highest mass among the planets, and it's so massive. The common rotation center of Jupiter and Sun is actually outside the Sun. So Sun is actually orbiting a point outside its radius, but that's only for Saturn. For the Jupiter. For other planets, Earth and other planets, the common center of rotation is inside the Sun. So we are orbiting the Sun. Jupiter is kind of technically not orbiting the Sun. The center is outside Sun. So now imagine this is a star far from Earth. Now we are here. We have telescope here, and we are looking at that. So because it is so far away, we cannot actually see the planet or the planet and star separately. So all we see is the star, and the motion, even though it is exaggerated in this diagram, star has maybe a radius, I don't know, thousands or maybe millions of kilometers. The size of the star varies. So we cannot see the motion of the star from Earth. So we cannot see like the star is going like here we have the star in the sky, and we cannot see it's going this direction and this direction. Like we cannot see the motion from Earth. So what we observe is actually the radial velocity. Radial velocity means the velocity of the star coming toward us in this direction. So we cannot see the motion in this direction because the star is so big and the motion is very small. We cannot see star from going left to right. But there's a way we can detect the radial velocity. In other words, the velocity toward us. So what we do is actually we get a spectrum of the light coming from the sun. So the light waves come to us. We can see it from telescopes. And when the star is coming toward us, it has a Doppler shift in frequencies of the light waves. So if it is coming toward us, we call it the blue shift because the frequencies are moved toward the blue side. And when the star is going away from us, we can see a red shift in its light. So this is called the Doppler effect. I think you all know about that. We can actually hear it when there's a vehicle or especially ambulance with the siren on going nearby us. We can see the frequencies are going higher when it is coming toward us, and when it is going away from us, we can hear the frequencies are going down. So this is the same thing, but not with sound, but with the light waves. So if we observe a star for a long duration of time, we can see the frequency of its light changes to the blue side and red side, blue side and red side. And if we can see a periodical pattern, which means the time it takes to complete one cycle is same for everything. It should be, because planet is going around the sun in same time period. We call the orbital period. It doesn't change So the red and blue shifts in those lights coming from the sun should change in here, and we have flat line here, and it takes so it cannot be like a random thing. So it should be a periodical difference of the frequency of the lights coming from the sun. So using the Doppler shift, we can measure the velocity of the star coming toward us and going away from us. So that's the radial velocity. We cannot measure the velocity directly. We measure the Doppler effect of the lights of the sun, star, and we can derive the radial velocity where the star is coming toward us and going away from us. So this is kind of top view, and this is like if we are looking at that solar system from Earth. So that's the viewpoint from us. And this kind of the diagram. So star is coming toward the Earth, we can see a blue shift, and when it is going away from us, we can see a red shift. So using these radial velocity components, we can identify there's a planet orbiting that star, because star is changing in a periodical, the star is moving in a periodical manner. So this doesn't require a very powerful telescope or anything like that. All we have to do is get the spectroscopic data of the light that's coming from the sun. So this is a kind of old method we used back in 90s, kind of those period. So this method has used practically to detect exoplanets. But with the development of new technologies, powerful telescope and algorithms that are used to detect exoplanets, we have a very popular method, as explained by the one member of the audience, we call transit photometry. So here we are actually looking at the star, and when a planet is going around that star, and if it crosses the planet from the field of from the direction that we are looking at it, we can see the light of these stars going down, because this is actually eclipse. We are this kind of a solar eclipse, but for another star. The planet is covering a portion of the star, so we can see a dip in its light. So it's kind of like that. So there's the normal light, and when the planet is moving across the disk of the star, we can see the dip, or the brightness is reduced a little bit, not like a solar eclipse. So I think you can understand, in order for this method to work, planet has to move between the sun and the star and the earth. So it has to align its orbital plane precisely with the earth. Otherwise, we cannot detect using this transit photometric method. But in radial velocity, the planet doesn't have to cross the disk of the star. All it had to move, so we can get the Doppler shift. But if we are using this method, the planet has to cross the star, the disk of the star, so we can see a dip in the light. So although now this is a popular method, it has a very big limitation. That's the alignment of the orbital plane with the Earth. And another important thing I need to point out, if we are using this method, when the planet is here, the atmosphere, the light from the star is actually coming through the atmosphere of that planet. So when we are observing that light from the spectrometer, we are getting the light from sun in this area, and we are getting lights through the atmosphere of the planets through this area. So once the planet is moved, we can get the clean light source from the star, and we can reduce those measurements. So we have to reduce planet atmosphere plus starlight from the pure starlight. So then we have the light went through the planet atmosphere. That information is so crucial, because now we have light just came through an atmosphere of an exoplanet, and we can get information about the planet atmosphere using that light, because certain molecules absorb certain type of frequencies. For example, let's say hydrogen absorbs a certain frequency of light. and oxygen absorb another certain frequency of light. So if we have those absorption frequencies in that light just came through a planetary atmosphere, we can say we have discovered hydrogen and oxygen, or potentially water, in that atmosphere. So we have maybe found a planet with water in the atmosphere. It could be water vapor or liquid water, I don't know, but we can simply identify it has hydrogen, oxygen, or maybe carbon and other kind of elements in that atmosphere using the spectroscopic analysis came from the observation of the planetary atmosphere. So, and another interesting method that are used to identify exoplanets called pulsar timing. So, do any of you guys know what's a pulsar is? Can someone tell me what's a pulsar? Yeah, please go ahead.
It's a neutron star which spins rotationally, and it also has, I think, a gamma ray burst or something. So when it spins, like, is that a pulsar? Basically, a neutron star which is emitting gamma ray bursts and it's spinning.
Yeah, that answer is
False.
yeah. So a pulsar is basically a neutron star, but it is kind of highly active in its radio emissions. There are some type of neutron stars that emits gamma rays, but most of those stars emit radio waves. So anyway, so these neutron stars rotate really fast. So they emit radio waves from its magnetic poles, so from the north side and the south side. So there are two emission beams going out from the neutron star, and when this rotates, we can see kind of we can see those radio waves when it faces the earth. So it kind of like kind of a beacon. So we can see those emissions of radio waves in a periodical manner. So if we take kind of a graph here, so we have time and the radio wave emissions. So it's kind of like kind of a pulse, because the rotational speed is a constant. We can see these pulses in constant time intervals, and it's kind of a pulse, so we call it a pulsar. The interesting thing is about this, these time periods are very accurate. Like, it's kind of similar to a accuracy of a second. So we can measure the rotation of that pulsar to a very precise manner. So we can say this pulsar rotate, it takes about this days, this minutes, and this seconds. So it is very accurate measurement. Now imagine there's a planets orbiting that pulsar. So what happened is, as I explained in the radial velocity part, this star moves because there's a planet orbiting the pulsar. Now what happened is, the pulsar is coming toward us and going away from us. So the distance between the Earth and the pulsar changes. So the time it takes for that radio waves to come to Earth, it also changes. We know for a fact that pulsar has a constant rotational speed. So if we see a periodical difference in the pulses, that means it has something orbiting that pulsar or neutron star. So now you might wonder, so this is kind of a radial velocity measurements. What's the difference? The difference is in radial velocity method, we are measuring the Doppler effect. That means we are looking at the difference in the frequencies of electromagnetic waves. So that difference needs to be kind of it has to be more than a certain number for us to be able to find it. So let's say it only changes 0.1 hertz. So it goes about 0.1 hertz and goes down another 0.1 hertz. So it's very small difference in the frequency, so limiting factors. But when we are measuring seconds and a time period, we can have much more higher accuracy. So we can detect the motion of the pulsar better than we can measure the radial velocity. That means we can detect smaller. Yes, Hamza.
Excuse me, sir, but the thing is, since pulsar emits gamma rays, and that is one of the highest frequency, what happens is it's very hard for like spacecraft to detect. So what do we do? So there's a very high chance that we could get a little bit like off measurements and things. So for that, what do we do?
I think as I explained before, pulsars emit both. Sometimes emit gamma rays, sometimes radio waves. Regardless, we can detect both of those. Like gamma ray observatories are not that uncommon. We have several spacecraft orbiting the Earth detecting gamma rays. So detecting gamma rays is not that difficult things. And in this method, we are basically measuring the time difference. So we are not focusing on the frequency difference, but we are actually looking at the difference in the time period between each pulses. So we can go to higher degree of accuracy with the pulsar timing than the radial velocity method.
Okay, thank you, sir.
So, okay, so the key advantage is the motion of the star depends on the mass of the planet. So if the planet is very big, the motion of the star is very big, but the planet is so small, the motion of the star is also very small. Using pulsar timing, we can detect a small motion. So as I have read, I think with the current technology, we can identify planet that's I think a 1/10 of the size of the Earth. So it's kind of a very precise method to detect a planet, but we need to have a pulsar to detect that. So that only works with pulsar. And I think this is the this method was used to detect the first exoplanet in 1992. So we use pulsar timing to detect the first exoplanet. And another interesting method used to detect exoplanet is gravitational microlensing. So I think you guys have heard about gravitational lensing. So gravitational lensing means basically so if somebody doesn't know what is okay, if somebody doesn't know what gravitational lensing, I will quickly explain that. So imagine there's a star here. It's a very distant star, and we are here, yeah, all the way here. So this is us looking at that. And we have another star between the distant star and us. So what happened is there's the light rays going every direction from the distant star. But due to the gravitational field of this star, these light rays bend and come towards us. So kind of like this. So gravity bends light. So that means we get a lot of more light rays from the star than if we get a straight line light rays. So if there wasn't any star in between the distant star and us, we only get light rays coming toward us. But in this method, we are getting much more light from the distant star because here the nearby star act as kind of a lens. So it collects more light from the distant star and focus toward us. So we can see that star better than we are looking it without the gravitational lensing. So now imagine this star is moving. So this is not a fixed star compared to this star. So this star moving in between us. So this lensing only happens when the distant star nearby star us aligns in a kind of a straight line. So in that moment, we can see a huge increase in the brightness of the distant star. So that is what we can see here. So that is the gravitational lensing. So microlensing part comes if there's a planet orbiting the nearby star. Once the main star create a gravitational lens, the planet can also create a small lens. So that's the microlensing part. So we can see two spikes in brightness, one from the gravitational lensing from the star itself, and then the planet cause also another small lensing. So it's a microlensing. So that is called gravitational microlensing, and it is also being used to detect exoplanets orbiting other stars. Another fun fact about this, in order for this to happen, we need to have a nearby star and a distant star. So in the sky, where we can find a lot of nearby stars and distant star, that is if we are looking at the center of the Milky Way. Because when we are looking at the center of the Milky Way, we are looking at a vast disk of stars to, I don't know, maybe 70,000 light years or something. I'm not sure. So if we are looking at the center of the Milky Way, we can see nearby stars and distant stars. So we can detect a lot of gravitational microlensing in that direction compared to other direction in the sky. So in these diagrams, I think these are the gravitational microlensing findings made by the Gaia spacecraft. I think you guys maybe heard about that spacecraft. That's from European Space Agency, and Gaia spacecraft has found a lot of gravitational microlensing exoplanets at the center of the galaxy. So in this animation, those are marked. And if we come to the modern day technologies and nearby future, we have another method called astrometry. Astrometry is a branch of astronomy. We are using other stars to find the position of a star very accurately. In the radial velocity, I told you guys that we cannot actually see the movement of the star from left to right. So I was actually talking about in the past with the old technologies. Using old technologies, we cannot do that. But modern and hopefully future technologies can identify those small motions of the star, and that emerging field is called astrometry. So using relatively fixed stars, we can see the relative motion of another star. So you can understand we need much powerful telescopes and much powerful softwares to detect these kind of microscopic motions in the sky. But we have that technology now, and hopefully in the future we can get much more better astrometric data. The Gaia spacecraft that I just mentioned earlier, it also doing astrometric observation in the stars in our Milky Way. So it's also mapping the three-dimensional position of a star in the sky. So when we are doing that for years, we can see those motion of a star, and if it is periodical, that probably means it has a planets orbiting that star. So we can say there's another exoplanet. So this is a modern technology. We didn't have the technology and the computational powers during 70s, 80s, 90s. Now we have this technology. And reflection emission modulations, another interesting method. So in the transit method, I told you that when a star is going in between the Earth and the star, we see a eclipse, kind of eclipse. So the brightness actually reduces. But what happens when the star is kind of at a side? Okay, let's say we are looking from the Earth and we can see the star. If the planet is here, we see a dip of light. The brightness of the star reduces because the planet is covering it. Now imagine the planet is here now. So what happens? So we only see the light rays coming from the star toward us. We cannot see light rays going toward this area, or here, or here. We cannot see those light rays. But let's say we have a planet here. So this is not to scale, only for explaining. So the light rays going in this direction falls on the planet, and we can see kind of a face like the faces of the moon. So this is the bright side and this is the dark side, and this area reflects those light rays toward us. So what happens is the light rays going toward this area, which were not supposed to come toward us, actually get reflected by the planet and come toward us. So if we are looking at from a top view, so we are here. So this is a eye, and planet reflects lights toward us. So what happened is we are getting direct rays from the star, and we are getting additional light rays from the reflected surface from the star. That means there's an increase in the brightness. So we have more light rays, which means more lights coming from the star and the reflected light from the planet. So it actually increases the brightness. Again, we have to observe this in a long period, so we can see, we can understand with the phases of the planet. So now imagine if the planet is in the position of kind of a new moon, Amavaka. So if the planet is here, what we are seeing is a dip of the light, because the planet is blocking a part of the light, and now planet is kind of a here. So we don't get much of reflected lights because the reflections are going in this direction. But if the planet is kind of a here, we can see kind of half of the planet. We cannot see the planet, but I am referring is the face. So the face is kind of a half from the viewpoint. So we are getting much more reflections. And now when the planet is here, it's closer to like the full moon day, full moon poe day, because the side of the daylight side is mostly facing us. So we are seeing much more reflections. So we are seeing like a big increase in the brightness. So once the planet goes behind the star, no reflections. So we are seeing only the light from the star. Once this one emerges from this side, again we have a good reflection. So we are again seeing a increase in the brightness, and as the planet come to here, the brightness slowly goes down, and once it's crossed the star, we are seeing a dip. So this is called a reflection emission modulations. So it is another method that are being used to detect exoplanets. These are actually not very popular methods because it's kind of hard for using these methods. And polarimetry. So this topic goes with the polarization of lights. And I think we are seeing some school students in the audience, so I think I have to explain what the polarization is also. Polarization means we all know like the light and other electromagnetic radiations or waves are actually electrical and magnetic waves that are perpendicular. So that's how we kind of define electromagnetic waves. So that's what illustrated here. We are seeing a electrical wave and a magnetic wave. So electromagnetic. So when a star emits electromagnetic waves, those waves goes in all directions. So we call it non-polarized waves because these wave patterns are in all directions. So it's kind of a here, 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 and every directions. So it's an unpolarized light. But we can have a polarizer, kind of a shutter or kind of a shade that lets only one direction of waves goes through it. So the output of a polarizer is basically a single polarization of a light. So it's a polarized light. So that's the principle behind the polarimetry. So when we are looking at the star, again back to astronomy. So we are looking at the star and we see unpolarized light coming from the star. That's normal because that's what happens. Now we have a planet here and it has reflections. What happens is the atmosphere of the planet acts as a polarizer. It kind of block some angles of the polarization, and we can see a polarized light coming from the planet. So we are getting non-polarized light from the star, and the reflected lights from the planet is polarized. So that's a property of the atmosphere, or the land, the surface of the planet itself can also polarize light with the reflections. So anyhow, we are getting unpolarized light from the star and polarized light from the planet. So we are getting mix of those lights using instruments, sophisticated instrument. We can kind of categorize those lights and understand, okay, we have a planet here, it polarized some certain part of light here, so that means it has atmosphere, or we can get the properties of atmosphere using those polarization. So it is also a unpopular method of detecting exoplanets. And one final thing, this only works with big planets. Imagine there's a massive planet going around a star. It can actually deform the shape of the star. So if the star is here, the planet is here, you can see the shape of the star is kind of stretched toward that. And if the planet is here, it's kind of a ellipsoid. So it deforms the star. So that only happens with the big planet. So this method is called ellipsoidal variations. That means we are looking at the shape of the disk of the star to see if it kind of a change. So it only applies for big planets. So these are basically some of methods that use for detecting exoplanets, and most of them are not familiar. Only the transit method and the radial velocity and the pulsar timings are kind of popular ones. I think now you can understand, in none of these methods we cannot see the planet. All we are seeing the light coming from it and the spectrum and everything. We cannot see the planet. We cannot resolve the planet. So maybe you see some news articles and some images in the internet. Oh, we have found a new planet, exoplanet, and you can see a planet kind of image. So these are computer generated images. There's no way we can see an exoplanet like that. Like, we can see the Jupiter, but we cannot see exoplanet like that in a manner. We don't have that kind of a instrument. But in modern day, we have some technologies to see the planet actually, but not very high resolution one. We call direct imaging. So what we do is basically, if we are looking at a bright light and we need to see another thing near that, what we do is we just cover the bright light so we can see the other object. So we use that method to actually observe the corona of the sun. So in the telescope that we use has a kind of a opaque disk that fits the size of the sun. So the photosphere of the sun is covered. We can see the corona clearly. So this method is called coronagraph. So this has been used to observe the corona of the suns for years. But wait a minute, can't we use this method to cover a star and see the planet orbiting it? So as you can understand, it's a very difficult thing because star is a very small thing. Even if we use a telescope, and planets are 1,000 or million times smaller than the star, so it's very hard to use coronagraph in to a star than doing with the sun. But with modern technology we can do that. This is a direct image of an exoplanet. I'm not sure whether this was taken from James Webb or Hubble or maybe Hale telescope. Oh, regardless, so the star is actually covered with a small disk, opaque disk, so we don't get glare or the star in the image. It's covered and we can see the planet. So this is a coronographic image of an exoplanet. So this is an imaging technology. This is like very kind of a new technology. James Webb has this technology, and Hale telescope, that's a ground-based telescope, it has this technology. And we will see more telescopes with the coronagraphs in the future. And another image, so star is covered with a disk, so we cannot see the star, and we have images from 3 planets. I don't know what happened to the planet A. Maybe the planet A is the closest one. So when we cover the star, it also hide behind the disk that we are using. So the distant planet B, C, D, and D are only photographed in this coronographic image. So this is the best we can do right now. So this is the best image we can get from a exoplanet. So we cannot see a detailed surface image like when we like what we take of Mars, Jupiter, and other planets. Those are all computer generated images, not real photos. These are real photos. This is how this is what we see as a exoplanet. So these are the methods and technologies that we use to detect exoplanets. So we have ground-based telescope and also space telescopes. So in today's session, I'm not going to talk about ground-based telescope. So what are exoplanet hunting spacecraft? We all know what this is. This is Hubble telescope. This is a very old telescope. It was launched in 1990. So it doesn't have very sophisticated technologies that were developed later. But there were some Hubble servicing missions until 2010. So that's kind of a new instrument up there, but it's not as modern as other telescopes. So this has been used to detect exoplanet, but we have much modern spacecraft. And this is the most favorite exoplanet hunter. This is the Kepler telescope. I think this was launched in 2010. I'm not sure. So this was specifically designed to observe exoplanets using transit method. So what it does is basically it observes a star for a long period of time, and using those data we can see the dip in lights, or we can understand if there's a planet. So this telescope has observed, I think, 530,000 stars, and data it sent to Earth. We haven't actually went through all of these. As of today, these these observation data are analyzed, and we will continue to do so for years because it has sent a lot of data. So we will continue to find new exoplanet using all data sent from Kepler telescope, because now it is not working. I think Kepler data from Kepler telescope has helped scientists to find more than 2,200 exoplanet. That is the largest number of exoplanet discovery made from data from single spacecraft. So this is the king of exoplanet hunting. And we have Spitzer telescopes, which is also not functional now. And this is a functional spacecraft. It's called TESS, Transient Exoplanet Survey Satellite or something. TESS, you can look it up. So it has 4 cameras, and it is orbiting the Earth. So it's a NASA space satellite, and I think it has fuel to operate for 3 more years, probably 2026, 2027. So it will continue to find an exoplanet for us. And the new kid on the block, we have James Webb Space Telescope. It has a coronagraph actually. So this can take direct images of exoplanets. So it's a modern technology. And this will probably be the next king of exoplanet hunting. This is the Plato spacecraft, which is slated to launch in 2026 from European Space Agency. And you can see it has a lot of cameras, I think 26 cameras. So this is a very unusual type of spacecraft, this with a lot of cameras looking at stars and trying to find exoplanet. So I hope this will find much more exoplanets. So it's under development right now, so it has 2 more years before launch. And before moving on, I need to talk about the orbits, because actually I can ask from you guys. So who can tell me what is the orbit of Hubble? Like, which object is it observing? What is the altitude of the orbit? Does anyone know? The orbit of the Hubble telescope. Nobody? Okay, the Hubble Space Telescope is at... Okay, Hamza, you can go ahead.
So I know the James Webb Telescope is orbiting at L2 point.
Yeah, it's actually the Sun Earth L2, because Lagrange points are at all two-body system. So James Webb is at Sun Earth L2 point, Sun Earth second Lagrange point. Hubble telescope is at low Earth orbit. It's coming down actually now, because nobody is raising its orbit. So it is, I think now it is around 500 or 550 kilometers. Probably it has few more years before re-entry the atmosphere if nobody fixes it. Kepler was at a heliocentric orbit, which means it was not orbiting the Earth, it was actually orbiting the Sun, and it was kind of following us. So it was placed in an orbit which is similar to the Earth orbit around the Sun. So we call it Earth trailing heliocentric orbit, which means it is going around the Sun behind us. So Earth is going around the Sun and the Kepler is coming with us, but in behind. So Earth trailing heliocentric orbit. And Spitzer was also in a kind of similar orbit. TESS is actually at a very high Earth orbit. It's elliptical orbit. It goes up to like 375,000 kilometers. So kind of toward the moon and back. So it's elliptical orbit. And James Webb is at Sun Earth L2 point, and Plato will be also placed in Sun Earth L2. So because the reason is, when we are looking at a star for a long time, it is difficult to do that if we are in a low Earth orbit, because in a low Earth orbit we are going around the Earth in 90 minutes. So 45 minutes you have the sunlight, another 45 minutes you have the night. So it is very difficult to take long observations, continuous long observation in Earth orbit. That's why we are going to heliocentric orbits or Lagrange points. In those places we can get much more long period of observations. And this is the new telescope which will be launched in few years. This is the successor of maybe James Webb, I don't know. So does anyone know the name of it? The new telescope of NASA.
Chandra-Ray.
Excuse me? I couldn't hear it.
Chandra X-ray.
Sorry, actually a Chandra X-ray telescope is actually in orbit. It was launched way back in the 90s.
Sorry, Roman.
Yeah, Roman. That's right. This is the Nancy Grace Roman Space Telescope. If you guys don't know who Nancy Grace Roman, she was the mother of Hubble telescope. So she was the director of the space observation department. Let's say department. So she was the head of space observation department in the NASA. The title is wrong. So she's called the mother of Hubble telescope because she worked so hard to get funding and other stuff approvals to get to start the project of the Hubble Space Telescope. So she's the mother of Hubble telescope. Now there's a telescope named after her. So Nancy Grace Roman Space Telescope, which will be launched, I don't know, I'm not sure, 2026, 2027, kind of like that. So this has a much more advanced coronagraphic camera. So that's what I want to tell you. So this will also looking at exoplanet discoveries. So okay, we have a question. What is the best orbit that can be used to park satellites to take information about exoplanets? So as I was saying, if we are using kind of a transit method, we need long period of observations. So we can do that in low Earth orbit, but it will not be continuous because we are going around the Earth. So we have to stop, go again, stop, go again, kind of that. But if we are in a Lagrange point, or L2 specifically, we can have our telescope pointed at a star for a long period of time. So it will be much more better quality of data. So that's why most of the space telescopes that focus on exoplanets are going to L2, and Nancy Grace also going to L2. So there will be James Webb, Gaia, Herschel, Plato, and Nancy Grace. All of these space telescopes are and will be in Sun-Earth Lagrange 2 point. And this is just a proposal, because now we have big rockets like Starship. We can launch much more bigger telescopes with very big primary mirrors. So these are not approved or under development. These are just concept and proposals. But in the future, we might see a big telescope. Compare, like if we compare this telescope to the James Webb will be much small. So with the with the advancement of the rocket technologies, we can get much better space telescopes up there. So maybe in 2030s or something, we might see this kind of a telescope. So not yet approved. Okay, the last part. So AI. So how can we use artificial intelligence in detecting exoplanets? So one method, so one application is we can use AI to control the spacecraft in much more in a precise way. So the telescope will be pointed at a star very precisely without motions. So like this is not a very crucial thing, because even without the artificial intelligence, we can control the the pointing accuracy, the direction we are looking at. We can control it with modern sensors. So it is not like a big game changing thing with artificial intelligence, but using artificial intelligence, we can kind of revolutionize the observations, because this is discovery of exoplanets plotted with the Earth the year. So in 1992, that was the first year we discovered the exoplanet. And as I told you, radial velocity was the old technology that used. And like in 24, 27, and we can see the rise of transit method. And in these years, like in 2016, that's the year with the largest number of exoplanet discoveries, because we had the Kepler telescope. So it's 1,534 new discoveries. So after the Kepler telescope retires, we can see the dip in discoveries. So, but you can understand with the development of the observation optical technologies, transit method has become the most popular method. So what can AI do to help us when we are using transit method? Okay, so when we are explaining the transit method, what we say is, okay, here we have the plot, we have the time, and this is the brightness. So we are seeing a little, dip in the brightness in a periodic manner. That is because there's a planet orbiting the star. So this is the like educational method. This is how it works. This is a theoretical explanation. But in practical terms, this never happens. What happens is we cannot take like a continuous video, we cannot take videos in spacecraft. So what we do is we take instantaneous or some short period of times observation, and it's a discrete observation. We take observation, we stops, we take another observation, we stop, kind of like that. We don't take videos. Like some people might think, okay, we are looking at the star, we are taking a video, okay, now we can see the dip in the brightness and it is up again. That never happens. So we are taking observations in a discrete manner. Discrete means it is not continuous. So what happens is we are seeing here, 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 and okay, we are seeing dip, and okay, we have again straight line, again dip. So this is kind of practical thing that happens. You might think this happens. Again, this doesn't happen in real world because we have the motion of the motions in the spacecraft. We have the natural variation of the brightness of the star. So this brightness of the star also varies without the planet, but we cannot see that in our eyes. The reason is those changes are very small, and okay, now the thing is, even though we plot a graph like this, the real decrease in the brightness is kind of a 1 in a million. So let's say now here, now if we draw the plot with to scale, so this is the brightness of the star, and there was a dip, and there was a dip, and there was a dip. You cannot see the dip, right? Because the dip here is very small. Like compared to the brightness of the star, the reduction is so small. If we draw the graph in with the scale, we cannot see. So when we zoom into the top level, we can see natural variations of the sun, the starlight. So it's kind of like that. So in a macroscopic level, we see a constant level of brightness, but in a very microscopic level, if we are looking at only the brightness, we can see variations. And there's the dip. So there's the natural variation of the brightness of the star, and there's the transit of the planet. So how can we like differentiate this? This is the difficulty of the data processing. Okay, now this is a real observational data. So these dots represented data points that we take in the relative flux. That's the scientific term that we use to measure the brightness. And it's all over the place because there's natural variations, there's the noise from the spacecraft sensors. It's not perfect. Those measurement instruments are not perfect. It has noise. Noise means unnecessary data points that coming from the measurement devices. So it's kind of all over the place. So we have scientists have developed computer algorithms to go through all of these data points and get a curve that fits the data. If you cannot understand what I just said, this is about curve fitting. If you have heard, okay, now we are plotting a table. We have data points. We have here, we have here, we have here, and we are told to find a straight line that fits these data points. So we can draw something like this, right? So yeah, so this is kind of, yeah, okay, this is a reasonable curve. So we are the name of this process is called curve fitting. We are trying to find a curve that fits to the data points. So there are various methods. one of the most popular one in maths is called least square method, but that's difficult. So that's the name here. If anyone is wondering what the least squares means, it's algorithms that use to fit a curve to data points. So the difficulty is now when a computer program is trying to fit a curve, okay, we have dip here. Is that a brightness reduction due to a transit of a planet? Probably not. And we have another dip here. We have another dip here. Okay, another one. We can have so many brightness reduction in these data points. So how can we find the correct one? Like, what is the curve caused by the planet? So that's what we have to find. So here also we can see another dip, and here that's the largest dip. So that's we call local minimum and a global minimum. So there are a lot of local minimums. Local minimum means there's a dip, but it's in a small area. So it's a local minimum, and the global minimum is the big one. So if we are doing this, if we are human and we have data, and if we look at this, oh, we can clearly see, okay, this is the big dip. Done. There's a planet. But we are running through a computer programs. It has to go through local minimums. It has to go through global minimums and a lot of computational process. And sometimes human have to, monitor the process and kind of thing. So it's a labor-intensive process. So that's the biggest help we can get from artificial intelligence. The deep learning of artificial intelligence is much more capable of handling these kind of things, because pattern recognition is one of the strongest abilities in deep learning. Deep learning is actually part of artificial intelligence, if you guys know that. So if we use deep learning, it will do this data processing much faster to find what are the sensor noises. So it's not useful, and these are natural variation of the brightness of the star, so it is not exoplanet, and go through all this data and find the dip in the brightness that caused by the planet transition. So deep learning is a much better tool for this particular application, and that will be the biggest help, because this is the most popular method of finding exoplanet, the transit photometry. And if we have the data points from the telescope, the satellite, spacecraft, we can have a deep learning algorithm, or AI in simple terms, to find the best curve that fits these data points, so we can know for sure, okay, this is exoplanet. So that is the the biggest advantage we can get from artificial intelligence when we are using exoplanet discovery, because as you know, the telescope only can provide data points, brightness of the star, the spectrum, and finding the exoplanet comes down to the data processing part. So when we optimize these data processing algorithms and methods, we can find exoplanets much more efficiently and with more confidence, because sometimes we cannot say in 100% certainty, okay, this is exoplanet. Let's say there's a 50-50 chance this is a natural brightness dip of a exoplanet. So Using deep learning, we might be able to find those patterns in long period of observations, and we can, the probability or the confidence of these conclusions will be much higher if we use AI. So scientists are already using these deep learning algorithms for processing their data. So in the future, they will use it much more. And I think we have a question. Can satellite collect information about exoplanet which are orbiting around outer planets? So by the definitions of the International Astronomical Union, if a celestial body or astronomical body orbit another planet, it called a satellite or moon. So you cannot say exoplanet which are orbiting other planets. So the definition of the planet, exoplanet, doesn't match there. So it is a natural satellite or moon. So are there any difference of the informations captured by satellites orbiting around Earth and orbiting around other outer planets like Saturn? Okay, so basically he's asking the difference between the information we get from a satellite orbiting around. Oh, okay, I'm sorry. I think I misunderstood the question. So he's asking, what if we orbit our, space telescope or satellite around other planets, not Earth? So I'm sorry, I didn't understand the question earlier. So, are there any difference of the information captured by satellites orbiting around Earth and orbiting around other planets like Saturn? Okay. The thing is, we can send a space telescope to orbit Saturn or Jupiter or Neptune. Okay, let's say we are sending a space telescope to Neptune. Now the problem is these stars are like light years away from us. So whether we place a telescope in Earth or near Neptune, the difference of the distance to that star is minuscule, because the difference is like a few billion kilometers from Earth to Neptune. So but the stars are like light years away. So the difference that makes from the location of the telescope at Earth or at Neptune is not that big. But on the other hand, we get quite negative effect, because if the space telescope is at Neptune, data rates, the communication with the Earth and the space telescopes, which will be so restricted with the distance. So we cannot get more data from the space telescopes because it is further away from us. So I think you know that there's a Voyager spacecraft. Those are like 100 astronomical units away from us. We get only like a very small bit of data from those spacecraft. So getting an image from that distance is very difficult with the communication delays, with communication restrictions. So it is much better to have a space telescope closer to us, because we can have much more data rates with the communication aspect. And sending a space telescope away from us doesn't make any difference, because stars are far away. So the space telescope is not getting closer to that star in practical terms. Yeah, it takes 22 hours to get information from Voyager, and it is only few bits of information. we cannot get a 1 megabytes of image, like image from the Voyager. It's very difficult. And this image is, data point from probably Kepler telescope. Let's say from observations, you can see there are different kind of dips in brightness. So there are a lot of data points. We have to go through all of them. For example, here we cannot see a big dip. So we can see a small dip here, but we cannot be certain that dip was caused by a star. So you can see the data points, and we need deep learning algorithms to process this data. Otherwise it will be so much more difficult with labor time, here the cost of labor and everything goes up. So artificial intelligence can help us in this particular subject for data processing, and it will be a big help if we can implement those correctly to find exoplanets. And I think that's all I have to say about the topic, and I think you guys have questions. And there are 5 questions from the feedbacks from I like to answer quickly. What will happen if the all space missions become private sector projects? So that's a bad thing, because private sector only focus on profits. They are looking for ways to make money. So space exploration is not a way they can get profit, because we find 1,000 new exoplanet. What's the monetary value of that? Probably zero. So private space companies won't do any of that. So that's why those space telescopes and everything are handled by government sector, because government sector, they are not focusing on profits. So that's why the government sector of space exploration is very important. If we look only for profits, there won't be any space exploration. Space exploration is very hard to get profit out of it. So we can have space tourism. That's one thing. Space tourism is a profit-making business, but space exploration and observing stars, finding exoplanets, there's no monetary value in long near term. So if all space missions become private sector, we will see only profit-making projects. There won't be much more exploration rather than business. And why today's satellite technology is not powerful to capture dark energy, dark matter, and far away celestial objects. One thing is we have a very big limitation on size of telescope, because the rockets have fixed size. So James Webb, so the mirror of the James Webb had to be folded. I think you guys know that, folded, because the fairing size of the rocket is about 5 meters. So the telescope had to fit within a 5-meter diameter cylinder. That's why the mirror had to be folded. So there's a limitation we can have with the size of the telescope. So if the size of the telescope is limited, there's a limit we can, how far we can see and how faint object we can see. And dark energy and dark matter is different thing, because we don't know what those are. Dark energy and dark matter are actually, how can you say it? It's kind of a conceptual idea, because dark energy is something that expands the universe fighting the gravity. If there's not dark energy, the gravity will contract the universe, but something we don't know what that is, that's hence the dark. So the dark energy is expanding the universe. So scientists are looking what this is, what this energy is, but we don't know that. Because we don't know that, it's kind of hard to find it. And dark matter is also something like that. It doesn't interact with the electromagnetic waves. That means we cannot see that in visible lights, infrared light, or the radio waves, the gamma rays. It doesn't interact with electromagnetic waves. So that's why we call it a dark matter. So we need different type of observational methods. One thing we are using is we cannot see the dark matter itself, but we can see the movement of other objects. We can see and the trajectory or the orbits of those objects are altered by the dark matter. Dark matter have gravitational influence, so we can see the orbits are being altered with the dark matter, but we cannot see it. So that's another reason, because we cannot capture it in an image. It's dark. Dark means not like a dim or kind of a black. So some people think dark matter means kind of a black thing. It is not black. We cannot see it in any electromagnetic wave. So we cannot detect it in a direct observing method. And the second question is, but sometimes the main system, so how can robots fix it again? So for this question, I cannot give an direct answer, because without knowing the problem, like I cannot say like how this will be fixed. Okay, we have okay, money is yes, please go ahead.
සර් අපි ඔක්කොම ඩිස්කවරීස් ප්‍රයිවට් සෙක්ටර් කරොත් අපිට ඒක පාලනය කරගන්න පුළුවන් විදිහට මොන හරි ඩිසිප්ලිනරි තියෙනවද මොන හරි බෝඩ් එකක් තියෙනවද because අපි AI දැන් ස්පේස් ඩිස්කවරි වලට ජොයින් කරගන්න නිසා අපිට ඒක පාලනය කරගන්න පුළුවන් තත්ත්වයක තියෙනවද දැනට?
මම එක තමයි කලින් කිව්වේ ප්‍රයිවට් සෙක්ටර් එක කියන එක බිස්නස් කරන්නේ. එයාලට වැඩක් නෑ ඩිස්කවරිස් වගේ දේවල්. අපි ගත්තොත් ස්පේස් ෆීල්ඩ් එකේ ඉන්න ප්‍රයිවට් කම්පැනිස් එයාලා කරන්නේ ප්‍රොෆිට් කියන්නේ ලාභ ලබන්න පුළුවන් දේවල් විතරයි. එයාලා රොකට් යවනවා, මොකද රොකට් යවනවා කියන්නේ බිස්නස් එකක්. ඊට පස්සේ එයාලා මිනිස්සුන්ව අභ්‍යවකාශයට ගෙනියනවා, ඒක බිස්නස් එකක්. සල්ලි ගන්න පුළුවන්. එයාලා චන්ද්‍රිකා හදනවා, චන්ද්‍රිකා වලින් අපිට ඉන්ටර්නෙට් හරි නැත්නම් කමියුනිකේෂන් සැටලයිට් ටීවී වගේ සර්විස් එකක් දීලා සල්ලි ගන්න පුළුවන්. ඒ කියන්නේ ප්‍රයිවට් සෙක්ටර් එක බලන්නේ සල්ලි හොයන්න. ඒ කියන්නේ බිස්නස් කරන්න. එක්ස්ප්ලොරේෂන් කියන්නේ අභ්‍යවකාශ ගවේෂණය කියන එක එහෙම සල්ලි ගන්න පුළුවන් සබ්ජෙක්ට් එකක් නෙමෙයිනේ. දැන් අඟහරුගේ මොනවා හරි හොයාගත්ත කියලා කාටවත් ප්‍රොෆිට් එකක් නෑ. ඒක ජස්ට් අපේ සයන්ස් වලට සහ අපේ කුතුහලයට කරන දෙයක්නේ. එතකොට ගවර්න්මන්ට් සයිඩ් එකෙන් තමයි ඩිස්කවරිස් එක්ස්ප්ලොරේෂන් පැත්ත කරන්නේ. ප්‍රයිවට් සෙක්ටර් එකේ ඒකට ලොකු දායකත්වයක් නැහැ. සමහරවිට ප්‍රයිවට් සෙක්ටරෙන් හදනවා. ඒ කියන්නේ ජේම්ස් වෙබ් ටෙලස්කෝප් එක හැදුවේ නෝත්‍රොප් ග්‍රමන් කියන ප්‍රයිවට් කම්පැනියෙන්. හැබැයි එයාලා කරේ බිස්නස් එකට ටෙලස්කෝප් එක හදපු එක. NASA එකෙන් තමයි සල්ලි දුන්නේ. ඩොලර් බිලියන 25ක් කොහෙද නේ මට මතක නැහැ. NASA එකෙන් සල්ලි දීලා නෝත්‍රොප් ග්‍රමන් කම්පැනියෙන් ටෙලස්කෝප් එක හදලා ගත්තා. NASA එකෙන් සහ ඒකේ අනිත් පාර්ට්නර්ස්ලා තමයි ටෙලස්කෝප් එක ඔපරේට් කරන්නේ. ඒකට සල්ලි වියදම් කරේ ගවර්න්මන්ට් සයිඩ් එකෙන්. ප්‍රයිවට් සයිඩ් එකෙන් කරේ බිස්නස් එකට මේක හදලා දුන්න එක විතරයි. ඒ කියන්නේ ඒක තේරුම් ගන්න ඕනේ. ප්‍රයිවට් සෙක්ටර් කියන එක මේ අභ්‍යවකාශ ගවේෂණය කරන්න, වෙන ග්‍රහලෝක වලට අභ්‍යවකාශ යාන යවලා ඒ වගේ තියෙන සයන්ටිෆික් ඩිස්කවරිස් කරන්න යාලට උනන්දුවක් නැහැ. යාලට ඕනේ සල්ලි වන්න පුළුවන් විදියක්. ඒකනේ පෞද්ගලික අංශ කියන්නේ ඒකටනේ අපි. ඔව් සඳරු.
මට දැනගන්න පුළුවන්ද සැටලයිට් ප්‍රෝග්‍රෑම් කරන්න යූස් කරන ටෙක්නොලොජිස් මොනවද කියලා?
ඒ කියන්නේ ලැන්ග්වේජ් වගේද? කම්පියුටර් ලැන්ග්වේජ් වගේද?
ලැන්ග්වේජ් සහ ඒ අදාළ ටෙක්නොලොජිස් මොනවද කියනවා?
normally ඒක කම්පැනි වෙනස් වෙනවා ප්‍රෝග්‍රෑමින් ලැන්ග්වේජ් ඒකට මට කියන්නේ කිලින් කියන්න බෑගෙන මම දන්න සමහර කම්පැනිස් ඉන්නවා C වගේ ලැන්ග්වේජ් යූස් කරනවා හැබැයි හැමෝම කරන්නේ නැහැ මොකද එව්වා කම්පැනියේ ඉන්න ඉන්ජිනියර්ස්ලාගේ අයිඩියාස් සහ ඒ වගේ දේවල් නේ එතකොට මට කියන්න බෑ චන්ද්‍රිකා වලට යූස් කරන ලැන්ග්වේජ් එක මේකයි කියලා මම දන්නවා C යූස් කරනවා කියලා සමහරු බට් අනිත් කම්පැනිස් වෙනවා යූස් කරනවා වෙන්න පුළුවන් ඒ ගොඩාම ඉතින් ඇප්ලිකේෂන් එක සහ සැටලයිට් එක ප්‍රෝග්‍රෑම් කරන ඉන්ජිනියර්ස්ලා මත තීරණය වෙන්නේ එයාලා ෆැමිලිය නම් මොකක් ලැන්ග්වේජ් එකක් එයාලා එකකින් කරනවා එයාලා කැමැත්ත අනුව new technologies that using in satellite and sensors ඒක නිකන් වේග ප්‍රශ්නයක් එකපාර කෙලින් උත්තරයක් දෙන්න බෑ ප්‍රධාන වෙනසක් තමයි පහුගිය අවුරුදු 10 වගේ බැලුවොත් ඉලෙක්ට්‍රොනික්ස් ගොඩක්ම ප්‍රමාණයෙන් පුංචි වෙච්ච ඉඳන් මිනියචරයිස් වෙච්ච ඉඳන් අපි කුඩා චන්ද්‍රිකා කියන එක නැත්නම් ස්මෝල් සැටලයිට් කියන එක අලුත් ෆීල්ඩ් එකක් විදිහට ඇවිල්ලා තියෙනවා කියුබ් සැටලයිට් පිකෝ සැටලයිට්ස් ස්මෝල් සැටලයිට්ස් වගේ දේවල් මේ අවුරුදු 10ක් 15ක් ඇතුළත තමයි එකපාරම එන්න ගත්තේ එතකොට සැටලයිට් ඉන්ඩස්ට්‍රි එකට අලුතෙන් එකතු වුණ දේ මොකක්ද කියලා ඇහුවොත් එකක් තමයි ස්මෝල් සැටලයිට් කියන එක ඒකට මේන් රීසන් එක උනේ ඉලෙක්ට්‍රොනික්ස් කුඩා වීම දෙවෙනි එක තමයි මේ මෑතකදී ආපු මෙගා කන්ස්ටලේෂන්ස් කියන එක. ඒ කියන්නේ ඉස්සර සාමාන්‍යයෙන් චන්ද්‍රිකා යවද්දී චන්ද්‍රිකා ජාල කියලා දෙනවනේ කන්ස්ටලේෂන්. චන්ද්‍රිකා 10ක් 15ක් 20ක් 30ක් තියෙනවා මොකක් හරි එක වැඩකට. එක්සැම්පල් එකක් GPS චන්ද්‍රිකා ජාලය ගත්තොත් චන්ද්‍රිකා 28ක් හරි 24ක් 36ක් වගේ ගාණක් තියෙන්නේ. ඒකින් මුළු ලෝකෙ පුරාම අපිට නැවිගේෂන් ඩේටා කියන්නේ ලොකේෂන් එක හොයාගන්න පුළුවන් විදිහට ඩේටා දෙනවා. ඒකට කිව්වේ සැටලයිට් කන්ස්ටලේෂන් කියලා. චන්ද්‍රිකා ජාල වගේ දෙයක් මොකක් හරි. හැබැයි මේ බ්‍රෝඩ්බෑන්ඩ් ඉන්ටර්නෙට් දෙන්න සැටලයිට් ජාල කියන එක ආවට පස්සේ මෙගා කන්ස්ටලේෂන් කියන එක එන්න ගත්තා. උදාහරණයක් විදිහට ස්ටාර්ලින්ක් චන්ද්‍රිකා මේ වෙද්දී 6000කට වඩා පහළ පෘථිවි කක්ෂයේ තියෙනවා. කලින් තිබ්බිනේ 24 30 40 වගේ කෙලින්ම 6000ක්. තව 6000ක් යවන්න ඉන්නවා SpaceX එකේ. ඒතර 12000යි. චීනනුත් ඒ වගේ චන්ද්‍රිකා ජාල 3ක් යවන්න ඉන්නවා. එතකොට තව තියෙනවා 30000ක් විතර. වන්ඩ සටලයිට් නෙට්වර්ක් එකේ චන්ද්‍රිකා 600 ගණක් තියෙනවා. එහෙම බැලුවොත් ඔය මෙගා කන්ස්ටලේෂන්ස් කියන එකත් අලුත් දෙයක් චන්ද්‍රිකා වලට. ඊට අමතරව ඉතින් normal technology එකේ development එකත් එක්ක computers දියුණු වෙද්දී satellite වල පාවිච්චි කරන computers දියුණු වෙනවා. ඒ වගේ يعني electronic technology එක දියුණු වෙද්දී ඒකත් එක්ක directly satellite වල තියෙන ඒක electronics පැත්තට දියුණු වෙනවා. ඒක ඉතින් default වෙන දෙයක් නේ ඒක. මේගොල්ලෝ උදකලා වෙලා නැහැනේ ඒකෙන්. Clear explanation of orbiting. මේක නම් ටිකක් වෙලා යන වැඩක්. සරල එක්සාම්පල් එකක් සරල විදිහට එක්ස්ප්ලেইন කරොත් ඔබිට් එකක් කියන්නේ මොකක්ද කියලා මෙහෙම හිතන්න අපි කාලතුවක්කුවක් වගේ මොකක් හරි අරගෙන උණ්ඩයක් දාලා වෙඩි තියනවා. එතකොට ඒ උණ්ඩේ යම් කිසි දුරක් ගිහලා බිම වැටෙනවා. අපි විසි කරන වේගය වැඩි කරන්න ඒක යන දුර වැඩි වෙනවා. ඒකට හේතුව තිරස් අතර තියෙන ප්‍රවේගය හින්දා අපි ඉස්සරහට යනවා ගුරුත්වාකර්ෂණයෙන් පහළට අද ගන්නවා. එතකොට පහළට වැටෙන්න කලින් ඉස්සරහට යන දුර වැඩි වෙනවා අපි විදින වෙඩි තියන වේගය වැඩි වුණොත්. ඉතින් ඕක වැඩි කරගෙන යද්දී ඔයාලා දන්නවා පෘථිවිය ගෝලයක්. සමහරු පැත්තට කිව්වට පෘථිවිය ගෝලයක්. එතකොට වෙන්නේ ඕක එක වෙලාවක ඔහොම දුරට ගිහිල්ලා ඇත්තරම අපේ පිටිපස්සෙන් ආපහු එනවා. මොකද ගුරුත්වාකර්ෂණික පහළට අදිනවා. ඒක නවතින්නේ නැහැ. ගුරුත්වාකර්ෂණයෙන් පහළට ඇද්දට horizontal velocity කියන්නේ තිරස් වේගයෙන් හින්දා මේක ලොකු දුරක් යනවා. ඉතින් ඒ දුර පෘථිවියේ පරිධියට සමාන වුණාම ඒ කියන්නේ මේක පෘථිවිය වටේ රවුමක් යනවා බිම වැටෙන්න කලින්. සරලව ගත්තොත් ඕබිට් කියන්නේ මේක තමයි. ඔයාලා පොඩි කාලේ සූරපප බලලා තියෙනවා නම් හෙල්ල විසි කරද්දි ඕක තමයි වෙන්නේ. මේක තමයි නිකන් සිම්පල්ම ටර්ම් එක මේක එක්ස්ප්ලেইন කරන්න පුළුවන් මොකද්ද ඕබිටින් කියන්නේ කියලා. මොකද අපිට ටයිම් ලිමිට් එකක් තියෙන හින්දා අන්තිම ප්‍රශ්නය details of upcoming and launch satellite. මේ වෙද්දි පෘථිවි කක්ෂයේ තියෙනවා චන්ද්‍රිකා Starlink Chandrika Mahayadaha. So there are 6,000 Starlink satellites in orbit, and the second biggest constellation is OneWeb. It is also internet satellite network. There's 634 satellite, and everything else is like 10, 20, 15, 100 kind of thing. So we have telecommunication satellite for communication, Earth observation satellite, scientific satellites for carbon dioxide measurement, ocean measurements, clouds, those kind of scientific measurements, methane levels. What else? GPS satellites, navigation satellite, and Russian notion of GPS. We have GLONASS, China has Beidou, and Europe has Galileo. All four of these are navigation satellites. And we have military satellites that are classified, so we don't know what they are. Probably spy satellite looking at us, but it's classified, so officially we don't know. Upcoming, we will see more than 40,000 of satellites launched from America and China, focusing on broadband internet. So we have Starlink, and we have Kuiper from again America, from Amazon company, and 3 satellite networks from China, Guowang, G60, and Hongdu. So there will be more than 50,000 satellites in low Earth orbit, providing broadband internet service all around the world, and the rest will be another 2,000 or something for telecommunication, Earth observation, GPS, and everything else. And if you guys have any questions, this will be your time. If there's no questions, I will hand over this to organizing committee again.
Yeah, I think the audience questions are over. Thank you to all of you. Thank you immensely, Mr. Udara, for sharing your knowledge and inspiring us today. We are truly grateful for the time and wisdom you have imparted. Accept this token we give for that.
Thanks for inviting me. This has been fun.
As we reach the grand final of this extraordinary webinar, it's time to express our heartfelt thanks. I'm delighted to invite Kavisha Sandumini, the Assistant Manager of Satellite and IT Division, to deliver the thank you speech. Over to you, Kavisha.
Thank you, Adisha. I want to extend our deepest gratitude to everyone who joined us today. Your enthusiasm and engagement made this event truly special. On behalf of the Satellite and IT Division of SETS USA, thank you for your participation, and we look forward to seeing you at our future events. And don't forget to check out the feedback form we have shared in the chat box. Your input is invaluable of us.
Yeah, let's capture this moment forever. Please turn on your cameras, everyone. Let's smile big and make this memory to last a lifetime. Thank you all so much.
Thank you all for being part of today's exciting webinar. We hope you enjoyed exploring the future of satellite technology with us. Stay tuned for more events and updates. We have got great things ahead. With that, we officially conclude today's session. Have a wonderful night.